Hello everyone. So today we are starting the topic of some mechanical properties of fluid. 3 hours have been allotted to this particular chapter. In the first hour we will talk about fluid statics, in the second hour we will talk about fluid dynamics, and in the third hour we will talk about surface tension. So without wasting time, let's start learning from the first hour where we will talk about fluid statics. The first thing we need to talk in fluid statics is the term of density. What is density? Sir, we know density is nothing but mass upon volume. The symbol I will use for density is rho. The symbol I will use for mass is m, and the symbol I will use for volume is v. So rho equals to m by v. It goes without saying, a student aspiring for NEET must know what is the density of pure water. The density of pure water is 1000 kg per meter cube, and you should know it. They might not give it to you in the question. To remember this, think that if you have a cubical container of length, width, height, all 1 meter by 1 meter by 1 meter, then the volume of this container will be 1 by 1 by 1 meter cube. And within this container of volume 1 meter cube, you can fill up a fluid. How much fluid? 1000 kg of fluid. So you can fill up 1000 kg of water within this container of side length of 1 meter. Hence the density of pure water is 1000 kg in 1 meter cube. So 1000 kg per meter cube. Now here on the mixing of fluids, two type of questions are asked. The first type, they will give you something like, if two fluids of density ρ1 and ρ2 are mixed in equal volume, then what is the density of mixture? So we are mixing two fluids of different density ρ1 and ρ2, but we are mixing them by same volume. They are asking you what is the density of mixture. So let's say you have got this first fluid, the first fluid having a density of ρ1, the volume V. The second fluid having a density of ρ2 and having volume V. And you have mixed them up. So the mixture will have a volume 2V. Question is, what will be the density of this mixture? So you can say, if the mass of the first fluid is m1 and the mass of the second fluid is m2, so once I have mixed them, the overall mass of mixture has to be equals to m1 plus m2. And since density equals to mass upon volume, I can even say mass equals to density into volume. So the mass of this first fluid has to be its density multiplied by its volume, that will be ρ1V. The mass of the second fluid has to be its density into its volume, that will be ρ2V. And when you mix them up, you get a mixture whose density you need to find. We have called it density of mixture. Its mass will be its density rho mixture into its volume 2V. So from mass balance, you will say mass of first fluid ρ1V plus mass of second fluid ρ2V has to be equal to mass of mixture, which has to be density of mixture into 2V. Now bachcho, if you cancel out V and bring a 2 down here, you will get the density of mixture to be equals to ρ1 plus ρ2 by 2. Such a simple thing. Now they might ask you the same type of question but this way. They might say, if they are mixed by equal mass, you have got two fluids, the first one of density ρ1, the second one of density ρ2, and you are mixing them, but you are mixing them by equal mass. So you are mixing equal mass of both the fluids. So let's say this is the picture. You have mixed up two fluids of same mass m and m. The first fluid has a density ρ1, the second fluid has a density ρ2. When you mix them up, the overall mass of the mixture will be 2m. And your mission is to find the density of this mixture. How to find? So see, we can say density equals to mass upon volume. Yes. So volume has to be equals to mass upon density. I can find out what is the volume of the first fluid added. Let's say V1. I can find out what is the volume of the second fluid added. Let's say V2. And when we add them up, the overall volume has to be V1 plus V2. So we can say the volume of first fluid added is m by ρ1. The volume of second fluid added is m by ρ2, and the volume of mixture has to be equal to the mass of the mixture upon density of mixture, which will be 2m by rho mixture. So doing volume balance, you will say volume of first fluid m by ρ1 plus volume of second fluid m by ρ2 has to be equal to volume of mixture, that will be 2m by density of mixture. Now once you have written this, you can cancel out m and m and m. So you will get 2 by density of mixture equals to 1 by ρ1 plus 1 by ρ2. Now you can solve it further. You can write 2 by density of mixture equals to rho 2 plus rho 1, rho 2 plus rho 1 upon rho 1 rho 2. You can flip it both the sides, so you will get density of mixture by 2 equals to rho 1 rho 2 by rho 1 plus rho 2, and then you can bring the 2 up here. So you will get the density of mixture to be equal to 2 rho 1 rho 2 upon rho 1 plus rho 2. Simple thing. Now when I will talk about fluid statics, the term I will focus upon the most is the term of pressure. So we need to understand what is pressure and why do fluid exert pressure. But before we talk about why do fluid exert pressure, we need to understand what is the meaning of fluids. So fluids are the substances which flow. So which type of substances flow? So we have got liquids, liquids do flow. So liquids are a part of fluid as well as gases. When I say that we are learning fluid dynamics, we are not at all talking about gases. We will focus on liquids. So when I say we are learning fluid statics, actually we are learning liquid statics. We are not talking about gases here. We have talked about gases already in the chapter of KTG. So question is, why do fluids exert pressure? When we look at a glass of water, to us the water appears to be at rest. But are the molecules of water at rest on the microscopic scale? No sir, there are molecules of water and these molecules of water are moving. These molecules of water are not at all at rest. They keep on moving in random direction. As the molecules of water move, they go and collide with the wall of the container. Now just visualize one wall of container and one such fluid molecule. If let's say this particular fluid molecule goes and collide with the wall of container, then after the collision with the wall, the fluid molecule bounces back. Yes, sir. During the collision, a force will act along the line of impact, which will be the normal to the surface of container. So a force will be applied by the container wall on the fluid molecule as it bounces back along the direction of normal. So this is force on fluid molecule. Force on fluid molecule. Sir, by Newton's third law, if the wall applies some force on the fluid molecule will apply force on wall. Now, due to this collision and bouncing back, the fluid molecule applies the force on wall in the direction of normal to the surface. In the direction of normal to the surface. And this force applied by all the fluid molecules per unit area is called the pressure. It's not that there is only one fluid molecule in the fluid, right? There are many of them. So all of them are continuously moving, continuously colliding with the container wall and bouncing back. When they bounce back, their momentum change. So a force must be acting on the fluid molecule. So the fluid molecule must be applying some force on the container wall. This force per unit area is the pressure. So visualize a container containing fluid. The molecules of fluid are not at rest. They keep on moving in random direction. They collide with the wall of the container and bounce back. Due to the change in momentum of molecules, they apply some force on the wall. This force acting per unit area is called pressure. Now question is, in which direction fluid applies force? Sir, the fluid applies force along the normal to the surface. We define the infinitely small force applied by the fluid dF equals to the pressure of the fluid times the infinitely small area dA. So dF equals to P into dA. Now understand that pressure is a scalar quantity. Pressure is a scalar quantity and pressure can't be negative. So the direction of infinitely small force is same as the direction of infinitely small area vector. I will teach you this thing again when I teach you Gauss law. Remember that whenever I say area vector, the direction of area vector is taken normal to the area. The direction of area vector is taken normal to the surface area. So if you think of one small area on this container, the direction has to be taken perpendicular to the surface. So the infinitely small force acting equals to P dA, where dA is an infinitely small area in the direction perpendicular to the surface. But for our general use, we will keep on saying force equals to pressure times area. Force equals to pressure times area. But the actual definition goes like dF equals to P dA. Now we need to talk about something called Pascal's law. The Pascal's law tells us something important and you need to understand this. The Pascal's law says that in a closed confined liquid, if the pressure is increased at one point, the pressure at all point increases by the same amount. So if you increase the pressure at one point of fluid, the pressure at all points in the fluid increase by the same amount. So for example, let's say we have got this container. Okay, so and there is a fluid filled, and at the top of fluid we have got this piston. We can apply Pascal's law on closed confined liquid. So it shouldn't be open. The fluid should not be able to flow. The liquid should not be able to flow. In a closed confined liquid, if you increase the pressure at one point by certain amount, the pressure at all point will increase by the same amount. So let's say we already know that as we go down in the fluid, the pressure increases. So let's say at this point of fluid pressure is P1 and at this point of fluid pressure is P2. As we move down because of gravity, the pressure increases. So you know that P2 will be greater than P1. Now if we place a block of mass M on top of it, then because of the weight of this block, the pressure at all points will increase by the same amount, and that amount will be the excess pressure created because of the placement of this block. So at all points within this fluid, the pressure will increase by an amount mg by A. So the point where before placing the block, the pressure was P1, now after placing it will be P1 plus mg by A, where A is the area of this piston. And at the point where the pressure was earlier P2, now there the pressure will be P2 plus mg by A. So in a closed confined liquid, if the pressure is increased at one point, the pressure at all point increases by the same amount. This is the Pascal's law that you need to know. So now let's talk about variation of pressure with depth. We know that as we move down in a container filled with fluid, the pressure increases. But why does this happen? Think of 2 points within the fluid, a point 1 and a point 2. Let's say at point 1 the pressure is P1 and at point 2 the pressure is P2. Looking at the macroscopic scale, looking from outside on the large scale, the fluid appears to be at rest. No doubt the fluid molecules are randomly moving, but there is no net force on the bulk of fluid. So if we imagine a cylindrical volume of this fluid, then the net force on this cylindrical volume of the fluid has to be zero. Because of the fluid above it, there will be a force in downward direction because fluid molecules will be coming, colliding and bouncing back. So there will be a downward force. Because of the fluid underneath this imaginary cylinder, there will be a force in upward direction because the fluid molecule will come, collide and bounce back, and in this process they will apply a force in the upward direction. And because of the fluid present on the side, there will be a force perpendicular to the surface, and this magnitude of force will keep on increasing as we move down because the pressure increases as we move down. So if we think of the force profile on this imaginary element of fluid in the shape of cylinder, from the fluid above it, there will be a downward force P1A. Because of the fluid below it, there will be an upward force P2A, and because of the fluid present on its side, there will be force perpendicular to the cylindrical wall which will keep on increasing as we keep on going down. Since in the macroscopic scale the fluid appears to be at rest, this means that in the macroscopic scale the net force on this fluid has to be zero. So the net force in upward direction has to be equals to net force in downward direction. There will be, in addition to these two forces of pressure P1A and P2A, there will be one more force of gravity in the vertical direction. So you can say the net force in downward direction, which is P1A plus mg, has to be equals to the net force in upward direction, which is P2A. Or bachcho, you can write, bringing this P1A to the right hand side, P2A minus P1A. The net force in upward direction has to be equals to mg. And in place of mass, you can write the mass of the fluid within this imaginary cylinder. The mass of the fluid within this imaginary cylinder has to be equals to density into volume. So you will get, for the net force on this imaginary cylinder to be 0, P2A minus P1A has to be equals to mg. And in place of mass, you can write density into volume, rho into AL. So you get P2A minus P1A equals to rho into AL into G. Now you can cancel out A. So you get P2 minus P1, which is delta P, equals to rho GL. Or you might have learned P2 minus P1 equals to rho GH. When you go a height H below, the pressure increases by rho GH. Right? You know that already. So let's move on and see a question. What length of water column will create a pressure difference of 1 atm? What length of water column will create a pressure difference of 1 atm? So we know that 1 atm is same as 10 raised to the power of 5 Pascal. It is slightly different from 10 raised to the power of 5 Pascal. It is 1 point something something into 10 raised to the power of 5, but we approximate it to 10 raised to the power of 5 Pascal. Now 1 Pascal is 1 Newton per meter square. Pascal is the SI unit of pressure. So question is, what length of water column will create a pressure difference of 1 atm? We know that if we have a water column of length L, then the pressure difference created by it is rho GL. So what length of water column will create a pressure difference of 1 atm? So here you will say delta P equals to rho GH. So 10 raised to the power of 5 equals to density of water 1000 into G, 10 into the height that we need to find. So substituting, you will say density of water is 1000. So 10 raised to the power of 5 equals to 10 raised to the power of 3, which is the density of water, into G, which is 10 into height H. So you will get from here H equals to 10 raised to the power of 5 divided by 1000 divided by 10. So height comes out to be equals to 10 meter. So remember that 10 meter of water column creates a pressure equals to 1 atm. We have already uploaded a video that even Superman can't drink using a straw more than 10 meter of height. I recommend you to go and watch it if you haven't already. Now, you need to remember this particular figure in mind, that 10 meter of water column creates a pressure of 1 atm. So if let's say we have a lake filled up with water, at the surface, the pressure is 1 atm. So if we think of a point on the surface of this lake, let's say A, then at point A, at the top, there will be no change because of the height of the fluid. So the pressure at point A will be nothing but P atm. So pressure at A equals to P atm, which is 1 atm. 1 atmospheric pressure, which is 10 raised to the power of 5 Pascal. Now visualize a point B below point A at a depth of 10 meter. So at this point B, which is at a depth of 10 meter, because of the water of length 10 meter present between them, a pressure difference would have been created. And we have just learned that 10 meter of water column creates a pressure difference of 1 atm. So at point A, the pressure is 1 atm. On moving 10 meter down within water, the pressure will further increase by 1 atm. So at a depth of 10 meter below the surface, the pressure at point B will be 1 atm due to atmosphere plus 1 atm due to 10 meter height of fluid. So the pressure at point B will be 2 atm. Similarly, if you think of another point C at a distance 10 meter below B, so going from B to C, again because of the presence of 10 meter of water column, the pressure will further increase by 1 atm. So the pressure at point C will be higher than that of at point B, again by 1 atm, so you will get 3 atm. And at point D, again at 10 meter below C, the pressure will again increase by 1 atm, so the pressure at point D has to be 4 atm. So remember that every 10 meter length of water column creates a pressure equal to 1 atm, which is 10 raised to the power of 5 Pascal. Let's see next question. Question goes like, there is this container in which you have got two fluid. The upper fluid has got density ρ1, the lower fluid has got density ρ2. The height of the upper fluid is H1 and the height of the lower fluid is H2. If the atmospheric pressure is P atm, if the pressure due to the air here is P atm, question is determine the pressure at point B and C. So we can say one thing, because the container is exposed to atmosphere and in the atmosphere the pressure is P atm, so the pressure at point A will be P atm. So how to write the pressure at point B? Going from point A to point B, we move down in a fluid of density ρ1 by a height h1. Because of this fluid, a pressure difference will be created and that will be equals to rho gh, so ρ1 gh1. So pressure at point B has to be equal to pressure at point A plus rho 1 GH1. So pressure at point B equals to pressure at point A, which is P atm, plus rho 1 GH1, that is the pressure difference created when you move a height h1 down in a fluid of density rho 1. Similarly, the pressure at point C will be equal to pressure at point B plus rho 2 GH2. So pressure at point C equals to pressure at point B plus rho 2 GH2. And you can substitute from the first equation what is the pressure at point B. Pressure at point B is P atm plus rho 1 GH1. Hence you get the pressure at point C can also be written as P atm plus rho 1 GH1 plus rho 2 GH2. P atm here moving down plus rho 1 GH1 plus rho 2 GH2. This is how you can write the pressure at point C. If let's say this whole system is placed inside a lift going up with an acceleration A, then how will you write the pressure at point B and at point C? So if this whole system is placed inside an lift going up with an acceleration A, then in place of G Manometer, everywhere use G plus A. Why? Because for a lift going up with an acceleration A, the G effective comes out to be G plus A. For a lift going down with an acceleration A, the G effective is G minus A. If you do not know how we get this G plus A and G minus A, look at the pseudo force part in the Newton's laws chapter. So the pressure at A will be still P atm, but when we write the pressure at B, in place of G, we should use G plus A. So you will write the pressure at B equals to pressure at A, which is P atm, plus rho 1 G plus A into H1. In place of G, just substitute G plus A. Similarly, the pressure at C now will be P atm plus rho 1 G plus A into H1 plus rho 2 G plus A into H2. So the pressure at C equals to P atm plus rho 1 G plus A into H1 plus rho 2 G plus A into H2. So if the lift goes up with an acceleration A, everywhere in place of G substitute G plus A. If the lift goes down with an acceleration A, everywhere in place of G substitute G minus A. Easy? Let's move on. Now let's say they have got you this U tube, and on the left hand side there is 10 centimeter of oil, and on the right hand side this 10 centimeter of oil is balanced by 8 centimeter of water. The question is, determine the density of oil. So if 10 centimeter of oil is balanced by 8 centimeter of water, how to write the density of oil? Now these type of questions are super duper easy. I am telling you one way which I will even use in current electricity. In current electricity, when we have a circuit, how do we write the equation of KVL? So we start from one point, come back to the same point and say that the potential difference is 0. Or we start from one point, come back to the same point and say the final potential is same as the initial potential. So what I do from in these type of question, I start from atmosphere. Start going downwards. As I go downwards, the pressure increases. Then I start going upward. As I go upward, the pressure decreases, and finally when I reach the atmosphere, the pressure drop is 0. So the final pressure is same as the initial pressure equals to P atm. So in all these type of question, I will start from a point, I will go down into the oil, the pressure will increase. Then I will go further down into the fluid, the pressure will further increase. Then I will start moving up, the pressure will decrease. Then I will move further up, the pressure will decrease, and I will say on coming out the final pressure will be P atm, and I will start with P atm. So let's see how to write the equation. So assuming the height of the water below the oil level to be h, assume that this much height of water is h. We will write P atm, the pressure here P atm, plus density of oil into G into H, density of oil into G into H, which is 10 centimeter, plus density of water into G into H. So you have reached this point. So at the top pressure is P atm. At this point pressure is P atm plus density of oil into G into H, this much part. Now if this height of fluid is H, then at this point you are moving further down, and as you move down in the fluid, because of gravity the pressure increases. So at this point, lowest point, you will write the pressure as this much term. How? P atm at the top plus rho oil G into 10 plus density of water into G into H. Now start going up. When you go from this point, let's say X, to this point Y, you are going up in the fluid. So the pressure will decrease by how much? Density of water into G into H. And then you go further in the water up by 8 centimeter. So when you are going down in the fluid, the pressure increases. So if you are going up, the pressure will decrease, minus density of water into G into 8. And now you have again reached the surface. So here the pressure will be P atm. So you will write the equation stating one more time. P atm plus density of oil into G into 10 plus rho GH minus rho GH minus rho G into 8 equals to P atm. Now bacho, you can see on both the side P atm get cancelled. This rho GH which got added while moving a height h down in the fluid gets subtracted with rho GH, which is the decrease in pressure when you went up a height h. So what you get is density of oil into G into 10 equals to density of water into G into 8. And you must know what is the density of pure water, 1000 kg per meter cube. So you get density of oil into 10 equals to density of water into 8. Cancel out Gg also. So density of oil into 10 equals to density of water into 8. So what you get from here is density of oil equals to density of water 1000 into 8 upon 10. Now you can cancel out this and this. So density of oil comes out to be 800 kg per meter cube. Easy thing. Do not worry if you haven't understood. We will practice more questions of the same time. So next example. If a fluid of density rho by 2 and length L is filled in the left arm of U tube, determine the rise in the liquid level in the right arm. So here we already have a U tube filled with a fluid of density rho. Now we are pouring a fluid of length L in the left arm such that this fluid has a density rho by 2. So because of pouring of this fluid, they are asking you how much the fluid will rise in the right arm. So let's say the fluid in the right arm rises by a height x. If the fluid in the right arm will rise by the height x, then this fluid of density rho will fall in the left arm by the same distance x, given that the cross-sectional area remains the same. So if the fluid in the right arm will rise by distance x, the fluid in the left arm will fall by distance x. Now, if you visualize the final condition, this fluid of density rho by 2 has a length L, and if this fluid of density rho rose a height x in the right arm, it will fall the same distance x in the left arm. So the difference in the height of the fluid of density rho in the two arm will be 2x. Now sir, how to find the value of x, which is our mission? So I will use the same method. Start from this point. Let's say here the pressure is P atm. Start moving down. So till here the pressure will remain same, equals to P atm, exposed to atmosphere. Going from this point till this point, you will say the pressure will increase as you move down because of a length L of a fluid of density rho by 2. Moving further down, the pressure will increase because you have moved a height h down in a fluid of density rho. Then going from this point up, the pressure will decrease because you have moved up in a fluid of density rho by height h. And then on going further up by a height 2x, the pressure will further decrease, and finally here the pressure is P atm. So you will write that assuming that the liquid of density rho rises by a height x in the right arm, so the decrease in the left arm is also x for the fluid of density rho. Right, we can write the equation as P atm plus rho 2 into G into L plus rho into G into H minus rho into G into H minus rho into G into 2x, this height will be 2x, equals to P atm. Now bachcho, you can easily cancel out P atm both the side, rho gx minus rho gx both the side, and you have got rho by 2 gl equals to rho g into 2x. So here you can cancel out rho and rho, g and g. So what you get is x equals to L by 4. So the fluid in the right arm will rise by a height L by 4. in the left arm will dip by a length L by 4. That is the basic idea. So let's see more application where I will make these same type of equation. So now we will talk about something called manometer. So what is a manometer? A device which is used to measure the pressure of a gas. So we take a container filled with a gas, connect a manometer to it. Sir, what is a manometer? A U-tube containing mercury. That is a manometer. And here we have got markings on the U-tube. So you can read how much the mercury level has increased or decreased. Now, when this valve is not open, this gas is not at all present in the tube. So the pressure on both the side is equal. So the mercury height on both the side is equal. But once we open the valve, then this gas starts coming out, and this gas is present even on the surface above the left hand side of mercury. Because of that, the pressure here becomes equals to pressure of gas. And as here the gas exerts the pressure, the mercury in the right arm will rise. Now let's say once the equilibrium is attained, the mercury level in the right arm is at a height h above the mercury level in the left arm. Knowing this reading of mercury level height, you can determine what is the pressure of the gas. How to write the equation? Easy. Here you will say the pressure is equal to pressure of gas. Let's say this height of mercury, below it is h. So you write pressure of gas plus rho g h minus rho g h minus rho g capital H equals to P80. So the equation goes like P gas here plus rho g h, pressure of this point, minus rho g h, pressure of this point, minus rho g capital H equals to P80. Since we know what is P80 and this rho g h can cancel, so we can say the pressure of gas minus P80 equals to rho into g into the height of the mercury. In the lab, what we measure is this particular height of mercury, how high the mercury has moved in the right arm compared to left arm. So if we know this reading h, we can find the pressure difference between the gas and atmosphere. And this pressure difference between the pressure of gas and the atmosphere is called the gauge pressure. So the gauge pressure is nothing but the pressure of gas minus the atmospheric pressure. So once we know in the lab what is the value of h, we can substitute the density of mercury into g into this height to know the pressure difference between the pressure of the gas and the atmospheric pressure. If you need the exact pressure of gas, then whatever reading you have got h, find out rho gh using it, and once you know rho gh, add P80m to it, you will get the actual pressure of gas. So the absolute pressure of gas is the gauge pressure. Gauge pressure, the pressure measured by the gauge. Gauge means the device used for measurement. So absolute pressure of gas is the gauge pressure, the pressure as measured by the instrument, which is rho gh plus P80m. So actual pressure of gas is gauge pressure plus P80m. Just move this P80m to right. Rho gh is the gauge pressure, so the absolute pressure of gas is the gauge pressure plus P80m. Easy thing. Let's move on. So now we will talk about hydrostatic paradox. It is a very simple paradox. So let's say you have got this random shaped container in which there is one tube which is cylindrical, another tube which is kind of a funnel, another inverted funnel, and a zigzag U-shaped tube. Now if we start pouring in water into one of them, any one of them, what happens to water? Since all of them are connected at the base, the fluid will spread out. So when you start filling in water through, let's say, any one of them, through the third one, the water starts spreading out as it starts filling. And at any given instant, the height of water in all four containers will be same, right? So if we pour in water in any one of them, the water will be distributed in all four as they are connected at the base, and the height of fluid in all four of them will be same. So if we fill in water at any given instant, the height of fluid in all four will be same, and the pressure at these 4 points A, B, C and D will be same. So what do you need to know? two simple things. First, the height of fluid in all the containers will be same because you are pouring in the same type of fluid. Second, the pressure at point A, B and C and D is same. Somebody might think that there is more amount of fluid above B, so there has to be more pressure at B, and that what creates the paradox. So the pressure at all 4 points is same, as if you start from here the pressure is P atm, you have to move a height h down to reach the point C. So at point C the pressure will be P atm plus rho gh. Same will be the case for point B, same will be the case for point A, and same will be the case for point D. So the pressure at all the 4 points A, B, C and D is same. So let's move on. Let's see a question. Question goes like, you have got 3 containers, okay, and all the 3 containers have the same base area. All the 3 containers have the same base area. Question is, if the same amount of fluid is filled in all 3 containers, if the same amount of fluid is filled in all 3 containers of same base area, the pressure at the base will be highest in which case? So if you are pouring in same amount of fluid, tell me in which case the height of the fluid will be greatest. So here, sir, when you have got funneled down for the same base area, height will be maximum. Then you will have the height in case of vertical cylinder, and the least height will be for this spread out container. Now the greater the height of fluid, the greater will be the pressure at the base. So you will say the fluid level will be highest in the case 2 because it is tapered as you go up, and lowest in the case 3 because it has got a broad frame. So less height of fluid for the same amount of fluid. Hence the pressure in the case 2 will be highest because the height of the fluid is highest, and the pressure in the case 3 will be least because the height of the fluid will be least, so the pressure at the base will be least. Moving on to another question. Question is, there is a horizontal tube. This horizontal tube is completely filled up with fluid. Question is, the tube is completely filled with fluid of density rho. This tube accelerates horizontally with an acceleration A towards right. Question is, what is the pressure difference between point A and B? And my personal favorite question here is, at which point the pressure is higher? So there are 2 points in this tube. One is point A, one is point B. This tube is completely filled with a fluid, and this tube has a horizontal acceleration A. Question is, at which point the pressure is higher, and what is the pressure difference between these 2 points? So sir, if we look at the fluid between the part A and B, since the whole tube, the whole fluid has an acceleration A towards right, even this much part will have an acceleration A towards right. So if we just consider this much part having a length L, because of the fluid on the left of A, it will push this fluid, and let's say the force will be PA, pressure at point A, multiplied by the area of the tube. And because of the fluid on the right of B, the molecules will come, they will collide and they will bounce back. So they will apply a force towards left, and that will be equals to PB into A. Since this much part of fluid trapped between A and B has a net acceleration towards right, it should have a net force on it towards right. And for the net force on it towards right, the pressure at A has to be more. So PA into A comes out to be more than PB into A. So let's understand this slowly once more. So if we just visualize the part of the fluid between A and B, on this much part of fluid, we will say this much part of fluid has a length L. It also has an acceleration A because it is moving with the tube. Because of the fluid on the left of the A, let's say at A the pressure is PA, so the fluid on the left will come, collide and bounce back. So it will apply a force towards right on this fluid, and that force will be PA into A. Because of the fluid on the right of the B, this fluid, the molecule will come, collide and bounce back. So these molecules will apply a force towards the left. Since this part of fluid accelerates towards right, there has to be a net force on it towards right. So you will say PAA minus PBA has to be the net force towards right. And this force has to be equal to mass of this fluid and element into its acceleration. So we can say as the given fluid accelerates towards right, the net force has to be towards right. So we can say the pressure at A has to be more than the pressure at B. Just remember this part. So if the tube has got acceleration towards right, then the pressure on the left has to be higher compared to the pressure on the right. Now you can say PAA minus PBA. PAA minus PBA. The net force in direction of acceleration has to be equal to mass into acceleration. The mass of this fluid element has to be equal to density into its volume. The density is rho. The volume is cross-sectional area into length. So the net force in direction of acceleration, PAA minus PBA, has to be equal to mass into acceleration, and the mass will be density into volume into the acceleration. Now in place of mass, you will substitute rho AL into A. Cancelling out A and A, you get delta P equals to rho AL. This is the solution. So PA minus PB equals to rho AL. The pressure on the left hand side comes out to be higher. So let's move on. So now the question. There is this U tube with the base part being horizontal and having a length L. And this whole U tube is being accelerated. Listen to the question carefully. The question goes like, when the U tube starts accelerating towards right, in which arm the fluid level will rise, and what will be the difference in the height in the two vertical arms? So initially in both the arms you have got fluid up to same height. When this whole system starts accelerating horizontally, in which arm the fluid level will rise, and what will be the difference in the height in the two arms at a later state? So how to solve this particular question? Simple question. Focus here. We know that if this horizontal part accelerates towards right, just focus on the horizontal part, and let's say the left end has a name A and the right end has a name B. So if the pressure here is PA and the pressure here is PB, if the horizontal part has an acceleration towards right, on it there has to be a net force towards right. Because of the fluid on the left, there will be a force PA into A. Because of the fluid on the right, there will be a force PB into A. If you want a net force towards right, then PA has to be more than PB. If you know that the pressure at point A has to be higher once it accelerates compared to pressure at point B, this means that the fluid level above A has to be higher than the fluid level above B. So finally, let's say the fluid level above A is higher than the fluid level above B by a height h. So the fluid level on the right arm will decrease and the fluid level in the left arm has to increase. Now our mission is to find this difference in the height. So how to find this? So you will say, in the horizontal part the pressure on the left end is higher. In the horizontal part the pressure on the left end is higher. So this fluid length has to be higher in the left arm. Now how to write the equation? Beta, start from this topmost point, PAT. Moving down, the pressure will increase on moving in downward direction because of gravity. So at this point A, you will write pressure to be PATM plus density of fluid into G into H plus H. Moving from A to B, the pressure will decrease. We have learned that due to the horizontal acceleration, the pressure difference is given by rho AL. So the pressure at point B, moving from A to B, will be written as PATM plus rho G H plus H, the pressure at point A, minus rho GL. Going from A to B, the pressure will decrease. So this quantity represents the pressure at point B. Now going from here up by a height h, again because of the gravity, when you move down the pressure increases, when you move up the pressure decreases. So you will say minus rho GH again equals to PATM. On the both the side, you can cancel out PATM, and this quantity rho GH minus rho GH will get cancelled. So what you get is rho G into capital H equals to rho AL. So you get rho GH equals to rho AL, but you cancel out rho and rho. Your mission is to find the height, so H comes out to be A into L by G. So H comes out to be A into L by G. So I will make the equation in the same way, entering from one point and exiting from another, and again writing the pressure equals to PATM. I will do it every time. So now comes the rock star of fluid statics, which is Archimedes Principle. What is Archimedes Principle? This one line you have to memorize by heart. So the line goes like, the upthrust applied by the fluid is equal to the weight of the fluid displaced. Once more, the upward force applied by the fluid is equal to the weight of the fluid displaced. Once more, the upward force applied by the fluid is equal to the weight of the fluid displaced. Okay. Now let's say we have got this mass and we have connected this mass with a spring balance, and this mass is suspended in air. Let's say the reading of the spring balance is mg. Once we submerge this same block into a fluid, then we know that due to the upward force applied by the fluid, the reading becomes less than mg. And if the surrounding fluid applies a force of upthrust equals to F up, then the new reading of this spring balance will be mg minus the upward force applied by the surrounding fluid. So how much is this upward force? So we know that from the Archimedes principle, the upward force is equal to the weight of the fluid displaced. The upward force is equal to the weight of the fluid displaced. So the force of upthrust equals to weight of the fluid displaced. But how to find what is the weight of the fluid displaced? This mass displaces a fluid of volume equal to its own volume. This mass displaces fluid of volume equal to its own volume. So if the block displaces a volume V, then the mass of fluid displaced will be equal to the density of fluid multiplied by the volume displaced. So the mass of fluid displaced equals to density of fluid into the volume displaced. So the weight of fluid displaced will be how much? So the mass of fluid displaced multiplied by g, because weight is nothing but mass by g. So remember that the block displaces fluid of volume same as its own volume. The block displaces, if completely submerged, the block displaces fluid of volume same as its own volume. Now, the mass of fluid displaced is equal to the density of surrounding fluid multiplied by the volume displaced. And the weight of the fluid displaced will be equal to the mass of fluid displaced into g. So just remember, the force of upthrust is equal to the weight of the fluid displaced, which is equals to density of surrounding fluid into volume submerged into g. So the force of upthrust equals to density of surrounding fluid into volume submerged into g. Once more, the force of upthrust equals to density of surrounding fluid into volume submerged into g. So now let's talk about floating bodies. If there is a body floating on a fluid, a body will float only when the density of the body is less than the density of fluid. If density of this body will be more than the density of fluid, it will sink. Okay. Now remember this thing. For a floating body, the force of upthrust has to be equal to the weight of the body. So for a floating body, the force of upthrust, the force of buoyancy equals to the weight of the body. We have just learned what is the force of buoyancy. The density of surrounding fluid into the volume submerged into g. So we can write the force of buoyancy as density of surrounding fluid into volume submerged into g. And how to write the weight of this body? So you will say the weight of the body equals to mass of the body into g. And one can write the mass of the body as density of the body into volume of the body into g. So you can write density of surrounding fluid into volume submerged into g equals to density of the body into v into g. Now cancelling out g and g on both the sides, you can say that the volume submerged upon the total volume or the fractional volume submerged to be equal to volume submerged upon the total volume equals to density of body upon density of surrounding fluid. Notice that the fractional volume submerged is independent of the acceleration due to gravity. So if we put this whole system into a lift accelerating upward with an acceleration a, or accelerating downward with an acceleration a, the g will change to g plus a or g minus a. But since the fractional volume submerged is independent of g, you will end up getting the same answer. So the fractional volume submerged equals to density of the body upon the density of the fluid. You can use this for floating bodies because in the case of floating bodies, only some part of the volume is submerged. So let's see a very nice question based on this. So the question goes like, if 2/3 length of the candle is inside water, 2/3 length of the candle is inside water, and it burns such that the length of the candle decreases at rate 3 centimeter per second. So the length of candle decreases by 3 centimeter every second. Question is, determine first what is the density of the wax used to make this candle, and second the rate of decrease of length of the candle above water. The rate of decrease of the length of the candle above the water. So you will say, see man, we know that the fractional volume submerged, the volume submerged upon the total volume of the body, the fractional volume submerged equals to density of body upon density of surrounding fluid. Here the candle is floating in water. So we know what is the density of the surrounding fluid, which is 1000 kg per meter cube. Now they have given me that 2/3 of the length of the candle is inside water and 1/3 is outside. So you can say if the cross sectional area is A, then 2/3 volume is inside in the fluid. So we can say the fractional volume submerged is 2/3 of total. So you will say the volume submerged cross sectional area A into 12 by 3 upon the total volume of candle, which is cross sectional area A into L. So the fractional volume submerged equals to density of wax upon density of fluid. So you will get 2 by 3 on the left hand side. A will cancel out with A, L with L. So 2 by 3 into density of fluid equals to density of body. So the density of wax is nothing but 2/3 the density of water, which is 1000. So you get the density of wax to be 2000 kg per meter cube. Now the second part of question. If this wax burns at the rate of 3 centimeter per second, question is the rate of decrease of length of the candle above the water. So you know that if the total length is L, then 2L by 3 is inside water and L by 3 is above the water. dl by dt is given to you as -3 centimeter per second, the rate of change of length of the candle with respect to time. We need to find what is dl by 3 upon dt because 1/3 of the total length is outside. dl by 3 dt, 1 by 3 is a constant, you can pull it out of the differentiation, so you get 1 by 3 times dl by dt, and dl by dt is -3, so you get 1 by 3 into -3, so you will get -1. So the rate of decrease of length outside will be 1/3 of the total rate of decrease because at any given instant only 1/3 is outside. So we can say no matter what is the length of candle, 2/3 will be inside the water and 1/3 will be outside the water. If the length of the candle decreases at the rate of 3 centimeter per second and 2/3 is inside, 1/3 outside, so the rate of decrease of length of candle inside the water will be 2 centimeter per second, while the rate of decrease of length of candle outside the water will be 1 centimeter per second. So if the length decreases at rate of 3 centimeter per second, then the length outside decreases at rate of 1 centimeter per second and the inside decreases at rate of 2 centimeter per second, because for any given length 2/3 will be inside, 1/3 will be outside. So if the overall length decreases at the rate of 3 centimeter per second, so the rate of decrease outside will be 1 and inside will be 2. So now let's talk the case when the entire body is submerged in a fluid. If a body is entirely submerged in a fluid, this will happen when the density of the body is greater than the density of the fluid. But we have discussed earlier also, once submerged, there will be a force of upthrust, a force of buoyancy. And the reading of this spring balance will be less than the weight. The reading of this spring balance will be actual weight of the body minus the force of buoyancy. So we say that once placed inside the fluid, the effective weight of the body decreases. So we say the effective weight of the body is nothing but the actual weight of the body minus the force of upthrust, the force of buoyancy. This force of buoyancy can be written as density of surrounding fluid into volume submerged into G. Since the entire volume of the body is submerged, here the volume V is nothing but the volume of the body. Now, on the right hand side here, in the term of density of surrounding fluid into volume submerged into G, forcefully multiply and divide with the density of the body. Why? You will understand, but do it. Now, once you have done it, this is what density of body, this is what volume of body, this is what G. Density of body into volume of body gives you mass of this body, multiplied by G gives you weight of the body. So combining these three terms, you can write simply one term, which is weight of the body. So you get the weight effective equals to weight of the body minus rho F by rho B, density of surrounding fluid upon density of the body into the weight. So you can take W common and you will get the effective weight equals to the actual weight into 1 minus density of surrounding fluid upon density of the body. Now, here the only doubt that students get is which value goes where. Beta see. This quantity has to be less than 1. Now. This quantity has to be less than 1. And if the body is submerged, we know that the density of the body has to be more than density of fluid. So remember that density of fluid in numerator and density of body in the denominator. So obvious thing, right? Let's move on. So you need to keep this particular formula in mind. It is useful at many different places. So the effective weight of the body once inside the fluid, given that the body has got density higher than fluid, is equals to the actual weight into 1 minus density of fluid upon density of the body. So a question here, there is a mass connected with a spring balance and there is a container containing water placed on a weighing balance. Question is, on submerging the block into the fluid, determine what happens to the reading of the spring balance and weighing balance. So if you place the weighing balance with the fluid and you submerge the block into it, then what happens to the reading of the spring balance and what happens to the reading of the weighing balance? Once you have immersed this block into the fluid will apply some upthrust. Since the fluid applies some upthrust, the reading of the spring balance will decrease. But what happens to the reading of the weighing balance? By Newton's third law, if the fluid applies a force on this block upwards, this block applies a force on the fluid downward. So think that you have a weighing balance over which you have a pan containing fluid, and if you start pushing it down, then the reading of the weighing balance will increase. So here, on placing the mass in water applies upward force. So the reading of spring balance decreases. I think till here you guys have no problem. Next part. From Newton's third law, the block pushes the water down. As the block pushes the water down, so the reading of the weighing balance will increase. So the reading of spring balance will decrease while the reading of weighing balance will increase. Next beta. The decrease in the reading of spring balance will be same as the increase in the reading of weighing balance. Or why? Because beta, the force applied by them on each other are equal and opposite. Newton's third law. So if a force of buoyancy Fb acts once immersed in fluid on the block upwards, the same force acts in the downward direction on the fluid. Hence, the decrease in the reading of spring balance will be same as the increase in the reading of weighing balance. Okay. Let's move on. Now let's say you have got this object trapped between two fluids of density ρ1 and ρ2. So question is, if the body trapped between the two fluid has 1/3 of its volume in upper fluid, so 1/3 of volume in the upper fluid and 2/3 in the lower fluid, determine the density of this body. So 1/3 of volume in the upper fluid and 2/3 of volume in the lower fluid, then what is the density of this body? You can see that this body has submerged in the upper fluid, but this body is floating in the lower fluid. This means that this body must have density more than ρ1 because it has submerged in the upper fluid. But this body must have density less than ρ2 because it is floating on the second fluid. So first thing we can say, let's say this body has a density ρ and this body has a volume V. As per the problem statement, 1/3 of the volume is submerged in the upper fluid, while 2/3 of the volume is submerged in the lower fluid. So assume the density and volume of the body to be V and rho, density of this body to be rho and the volume to be V. So you will say the density of this body must lie between ρ1 and ρ2. It must be greater than ρ1 because it submerges in ρ1, and it must be less than ρ2 because it floats on ρ2. So density of the body will lie somewhere between ρ1 and ρ2. Now from Archimedes principle we can say that the force of buoyancy applied by the upper fluid plus the force of buoyancy applied by the lower fluid equals to weight of this object trapped between them. So you will say the force of buoyancy by the upper fluid 1 plus the force of buoyancy by the lower fluid 2 has to be equal to weight of this body. The force of buoyancy by the upper fluid, if the overall volume is V and in the upper fluid you have got 1/3 volume, you will have V by 3. So you will write ρ1 V by 3 into G, plus in the lower fluid you will have 2/3 the volume, 2V by 3. So because of the lower fluid, the force of buoyancy will be ρ2 into 2V by 3 into G. So you will write ρ1 into V by 3 into G plus ρ2 into 2V by 3 into G equals to the weight of the body. And what will be the weight of this body? The weight of the body has to be equals to its density into its volume, that will be its mass, into G. So this has to be equals to rho Vg. Now bachcho, you can cancel out V, G. So what you get is ρ1 by 3 plus 2 ρ2 by 3 equals to rho. So rho comes out to be simply ρ1 plus 2 ρ2 by 3. Now there is one important caution point. This is not at all the right method to solve this question. But since we are getting the answer, who cares? So actually this method is not correct. But who cares as we get the answer, because the actual method is that the upper fluid do not applies an upward force on this body. The molecules of the upper fluid come, collide and bounce back. As they do, they actually applies a downward force. But because of the presence of the upper fluid, the pressure here increases even more, and that produces the same effect. So if somebody asks you what is the direction of force applied by upper fluid on this block, the answer is not upward, the answer is downward. But this method works, it's simple, and this type of question have came in NEET. The other method becomes long. That's why I recommend you to use this particular method. You will get the right answer for sure, have faith, but the method is wrong. So moving on to the next thing. Let's say we have a tube completely filled up with fluid, and this tube is being rotated about one of its end. Now there are 2 points A and B at distance r1 and r2 from the axis of rotation. Question is, if the tube is completely filled with fluid of density rho, determine between A and B where the pressure is higher and what is the pressure difference. So between A and B, where the pressure will be higher and what will be the pressure difference. When I gave you this example that there is a horizontal tube accelerating towards right, and I gave you 2 points A and B, I said that the pressure at A will be greater than pressure at B because on this much part of fluid between them, you must have a net force towards right? Similarly, better tell me, for the fluid trapped between A and B, what is the direction of acceleration? For the fluid trapped between A and B, what is the direction of acceleration? The whole tube moves in a circle. So this part of fluid also moves in a circle. And to perform a circular motion, you must have a net force towards the center. So if we visualize only the part of fluid between A and B, we will say since it performs circular motion, it must have a net force towards the center. Because of the fluid on the left of the A, there will be a force here, PA into A. Because of the fluid on the right of the B, there will be a force, PB into A. As the net force has to be towards the center, we will say that PB has to be greater than PA. So, as this section moves in the circle between A and B, a net force should act towards the center. So, if you just visualize this section trapped between A and B, on this section, because of the fluid on the left, there will be a force equals to PA into A, and because of the fluid on its right, there will be a force PB into A. Since the net force has to be towards the center because it performs circular motion, That's why we can say PB is greater than PA. It must have a centripetal acceleration. Now, how to find what is the pressure difference? We will go there. So hence we will say PB is greater than PA. Now, what we did in case of this horizontal tube? Sir, we said that think of the pressure difference, think of the force because of them, and that is equals to mass into acceleration. Here the problem is that each mass moves in a circle of different radius. So which point we should focus upon? We should focus upon the center of mass of this much length of rod. What will be the length of this rod? The point A is at a distance r1. The point B is at a distance r2. So the length of this section will be nothing but r2 minus r1. And the center of mass of this section will be at how much distance? So you will say this length is r1. And this length from here to here will be r2 minus r1 by 2. So the distance of the center of mass of this part from the hinge, from the axis of rotation, will be r1 plus r2 minus r1 by 2. That is 2r1 plus r2 minus r1 by 2. So 2r1 plus r2 minus r1 by 2, and that gives you r1 plus r2 by 2. So the radius in which the center of mass will rotate, that radius is nothing but r1 plus r2 by 2. And isn't it obvious? Point A at distance r1, point B at distance r2. The point exactly midway between them has to be at distance r1 plus r2 by 2. Now, this center of mass rotates in a circle of radius r1 plus r2 by 2. It has some angular velocity omega. So you will say the net force acting towards the center, PB minus PA into A, has to be equals to m omega square into r. What is m? The mass of this section. How will you write the mass of this section? Density into volume. So the density is rho and the volume is A into r2 minus r1, as the length of this section is r2 minus r1, into omega square, into the radius in which the center of mass rotates, and the center of mass rotates in a radius r1 plus r2 by 2 into r1 plus r2 by 2. So you will get rho A into r2 minus r1 into omega square into r1 plus r2 by 2. So bachcho, on both the side you can cancel out A and A. So you will get delta P equals to rho omega square into r2 minus r1 into r2 plus r1, give you r2 square minus r1 square. So you get delta P equals to rho omega square, and this part r2 minus r1 into r1 plus r2 gives you r2 square minus r1 square by 2. So this is the pressure difference between point A and B. In your NEET paper they will ask you maximum out of A and B which one has higher pressure. So remember that the pressure of B is more than the pressure of A, as this part moves in a circle, so there has to be a net force towards the center. Now if we take r1 equals to 0 and r2 equals to, let's say, r, so if there is one tube rotating about the axis and they ask you randomly what is the pressure at distance r, given that here the pressure is 0. So in place of r1 substitute 0, in place of r2 substitute r. So you will get, on substituting in place of r1 0, r2 r, you will get the pressure difference equals to rho omega square into r square minus 0 square by 2, that is rho omega square r square by 2. So now the last application we need to talk about is equation of vortex. If you have a container containing a fluid and the fluid is being rotated with some angular velocity omega, so we have seen that this fluid take up a curved shape. Now this curved shape is called vortex, and we need to write the equation of the curve. That will be called equation of vortex. So it looks like a tough thing, it's a very easy thing. So let's say we have got this container containing a fluid and the system is rotating with an angular velocity omega. We need to determine the equation of this particular curve. So assume the lowest point on this curve to be the origin. Now we need to find the equation of this curve. So go at a random coordinate on the curve, and let's say here the coordinate is x comma y. So along the axis you have moved a distance x, and vertically above from the origin you have moved a distance y. So this point will be x comma y. moving away from the axis horizontally, the pressure will increase because of rotation. And going from the atmosphere to the point P, the pressure will increase moving downward because of gravity. So you will say at this point which you have considered as origin and this point which is x comma y, at both the points, since both of them are exposed to atmosphere, the pressure will be P atm. So if you move horizontally from origin to point P, the pressure will increase because of rotation. Because this point P rotates in a circle of radius x with an angular velocity omega. And as you move from surface down, the pressure will increase because of gravity. So you can say the pressure at point P can be written as P atm plus rho omega square x square by 2 because of rotation. At origin, the pressure is P atm. Moving horizontally, the pressure will increase because of rotation, and we have just learned that if R1 is 0 and R2 is R, then the pressure at this point will be given as rho omega square R square by 2, right? So similarly here, the pressure at this point can be written as P atm plus rho omega square x square by 2. Similarly, the pressure of same point P can be written moving from the surface in downward direction. When we move in the downward direction, the pressure increases because of gravity. So we can write the pressure of same point P as P atm plus rho gy. Now equating these two, P atm get cancelled. So you will write rho gy equals to rho omega square x square by 2, or rho omega square x square by 2 equals to rho gy. Cancel out bachcho rho both the side. So you will get y equals to omega square x square by 2g. Sir, will NEET ask us this question? No. NEET will ask you this question. As y is proportional to x square, the shape of this vortex is parabola. So that's all what I wanted to teach. In the equation of vortex, you should just know that the shape of this vortex is parabola. See you guys in next hour where we will talk about fluid dynamics. Bye bye. So that's all for now. See you guys in the next hour.